Welcome to the third lecture of the course entitled Basics of Fluorescence Spectroscopy. So, in the last two class, we are discussing the basics of fluorescence spectroscopy itself. That means the introduction, brief history, and the light matter interaction, how it is going to excite the atoms or molecules by absorbing light, and so on and so forth. So, in the last class we finished with the excitation of atoms by electromagnetic radiation from one electronic level to another electronic level. So, today I will continue with this in case of the molecule, right. So, as told you earlier, the molecules will going to have different electronic energy levels, right, and each electronic energy levels is having a different vibrational levels. So, here I have showed the ground electronic level of a molecule, and where these are different vibrational levels. Right. So, and as I told you that according to the Boltzmann distribution and in the room temperature, the energy state of this molecule is the lowest electronic level as well as the lowest vibrational level of the lowest electronic level. So, the molecule will sit over here as shown over this yellow ball. Now, if I provide a suitable light whose energy is actually related with the energy difference between the ground and the excited electronic level, then this light can be absorbed. Actually, two conditions has to be satisfied for the light absorption. First, the light energy has to be same as the difference in the energy between the excited state and the ground state of the molecule. Like in this case, the incoming photon energy must be equal to the difference in the energy of this excited state and the ground state. Secondly, the transition moment integral should be non-zero, right. So, in this particular course I am not going to discuss in detail about this transition moment integral as of the basic nature of this course, and obviously this needs a little bit of knowledge on the quantum mechanics. Now, here you see here according to this particular diagram, I have excited this molecule from V equal to 0 of ground electronic level to V equal to 1, 2, 3, 0, 1, 2, 3, 4, V equal to 4 of the excited electronic level, right. It could be here also, it could be here also, depending on something which I will come after maybe 5-10 minutes. But anyway, so I have excited this molecule from here to here, right. I have excited the molecule from here to here. It means that, and also note here that I have written the excitation 10 to the power minus 15 second, which we already have discussed in the last class, that the time taken for absorption is about 1 femtosecond. In this, let me give you one example to comprehend this time. What is 1 femtosecond, right? What is 1 femtosecond, and how I am going to realize that word femtosecond. That femtosecond, right, the number of femtosecond in 1 second, that is what, 10 to the power 15, 10 to the power 15 femtoseconds consist in 1 second. Is that number is same as number of second present in 30 million years, number of second present in 30 million years, right. So, you see that how small it is, just this is to comprehend that number femtosecond. Anyway, so let us come to our discussion. So, here we have excited this molecule, right, from ground state to the excited state. Now, if I show you the structure of the molecule, this is the structure of the molecule, and these are the molecular orbital. Like in previously what I have showed you, that for atom there are different electronic orbitals of these atoms, and the electron moves from one orbital to the another orbital, that is for the atom. But for the molecule I have to talk about the molecular orbital, right. So, this is the different molecular orbital, this is HOMO, highest occupied molecular orbital, that is 2 electron is present over here, and this is LUMO, lowest unoccupied molecular orbital, that means it is a vacant orbital, right. Whenever I excite a system from ground state to this excited state, it means I took 1 electron from this HOMO and put it on the LUMO. It could be HOMO to LUMO, it could be HOMO -1 to LUMO +1, depending on the molecule to molecule, depending on this transition, whether some transitions are allowed, some are not, that depends on the transition moment integral, but I am not, as I said, I am not going to discuss all those finer details over here, just to give you the overall idea about this basic fluorescence spectroscopy. Anyway, so let's consider that this is ground state, this is excited state, that means 1 electron is taken from here and will put it in the LUMO, right. So this is correspondingly this transition. Now I am going to have this LUMO +1 also, and let's consider this LUMO +1 looks something like this way, this electronic cloud, right, in this molecular frame. Now if you put this electron from HOMO to LUMO +1, it's also possible, right, HOMO to LUMO +1, that means you are going to excite for this particular system from here to over here, this electronic state. Okay. So this is about this electronic transition in the molecule. This is about the electronic transition in the molecule. Okay. Now I want to show you that how we are going to measure the absorption spectra of a molecule.
I have a question.
Yes.
So what if HOMO to LUMO +1 is not allowed, then the H2 transition will not be present or something like that?
Yeah. So it's a good question. Some transitions are allowed, some are not, as we know, right. So if one transition is not allowed, let's say for example, his question is that if the HOMO to LUMO +1 transition is not allowed, then I am not going to see it in the experimentally. So then the next transition will be HOMO to LUMO +2, probably depends on the molecule. If it is allowed, then I will be able to see. It means that when I use a light of a particular frequency, let me tell you that frequency is nu1, let us say for example. So let me use a different color to make it clear for you. So in this particular case, I have used a frequency nu1. So I promote the system from ground state to the first excited electronic state, and when I used a frequency nu2, then I promote this system from here to here, right, from here to here. So if you use a frequency in between from between nu1 and nu2 whose energy is so that you will go from here to here, then that particular photon will not going to be absorbed by this molecule, right. So simply if I scan the frequency or if I scan the wavelength for this molecule, I am going to see a different peaks, right. So that is what we measure this absorption spectra of the molecule, right. So basically what we are going to do, I have to scan this wavelength. So this is important, I have to scan the wavelength, right. So the I0 is coming, it interacts with the sample and then it is passing through the sample. Depending on these electronic levels and the relationship between this energy of the incident radiation lambda, that is corresponding to some energy h nu. So some lights will going to be absorbed by the system, some light will not, right. And obviously this I, which is a function of lambda, is equal to I0 10 to the power epsilon, which is also a function of lambda CL. That means this is nothing but A, which is a function of lambda, is equal to epsilon, which is a function of lambda C, and the small l or capital L or CL, right. And this is equal to log I0 by I. These both are obviously the function of lambda, that is it, is not it. Okay. So, when I excite this, when I scan this thing, what I will get? I will get somewhere there is a lot of absorption of the light. So, the value of I is much smaller than I 0, let us say over here the value of I is smaller than I 0, here is much smaller than I 0, and in this case where it is 0, right, here it is 0, then in this case the I and I 0 are same, right. So, log 1 equal to 0, right. So, I got this 0 over here. So, the scan of wavelength and plotting it and plotting the absorption A or OD, this also known as OD. So, A or optical density OD is nothing but my absorption spectra. Now, you see here there are two different, clearly I can see two different transition. One transition is over here, another transition is over here, right. If the corresponding wavelength is lambda 1, if this corresponding wavelength is lambda 2, then let us see this molecular energy diagram over here. So, when I shine this light, this electron moves from one state to the other state, right. That must be corresponding to this lambda 1. So, here this light is H nu 1, and what is the relationship between nu 1 and lambda 1? Nu is equal to C by lambda. So, nu 1 equal to C by lambda 1. So, this particular transition is corresponding to this particular maxima in my absorption spectra. Now, when I change the wavelength of the light to the shorter wavelength, right, here wavelength is larger, here wavelength is shorter, shorter wavelength means the higher energy, as you can see over here. So, I excite this system from here to here, right. So, in this particular case this is H nu 2, where nu 2 is equal to C by lambda 2. So, I got this lambda 2 intensity, right. So, I got this lambda 2 intensity, so lambda 2 maxima in my absorption spectra, is not it. In this case the absorbance is more, in this case absorbance is less. It is related to this epsilon or and in consequence related to the absorption cross section of this molecule for these two different type of light, right. Okay. So, now in connection with this, let me discuss the shape of the absorption spectra, right, this is important. So, from this whatever I discussed, you have seen that if the energy is first of all the transition has to be allowed, which I have not discussed, please note that. So, for allowed transitions, which is defined by this transition moment integral, let us say this transition moment integral, according to that the transition is allowed, then it has to satisfy that delta E is equal to H nu, right, then only the transition is allowed. Again I have taken this simple atomic system, and here if you have this two level, the level 1 and level 2, there is no other level, right, there is no other level. So, if this E1, this is the energy E1, E2 sorry, and this E1, if E2 minus E1 equal to H nu, then the system will go from level 1 to level 2, right. And in this case if you plot here, what you want to plot, let me plot nu or lambda, whatever I want I can plot, and in this case if I plot absorbance, right, A. So, what I will get? I will get a sharp line like this, right, and this particular value is, let me write as 1 2, this value will be nu 1 2, is not it. Okay. But as molecules, as I said that it consists of many levels. Although for the electronic, these are the electronic, this is and these are the different vibrational. Although initially it stayed over here, the molecule state over here, but it can go at any level, it can go at any level if it is allowed transitions. Again I am telling that. So, it can go to the any level. That means, I am going to have a multiple transitions, multiple lines. That is for this simple example, I am going to have 1, 2, 3, 4, 5, total 5 lines over here. So, the spectrum will look something like this. Okay, let me redraw. This will look something like this, right. Again I am plotting this against nu, and I am plotting this absorbance over here, right. So, the spectrum in this case the spectrum is a sharp line, but in this case the spectrum with the vibrational structures. Now, this relative intensity of these different lines, right, they are not same in actually. So, the relative intensity of this vibrational part of an electronic absorption band can easily be rationalized by the Frank-Gordon principle. So, what is Frank-Gordon principle? Frank-Gordon principle is based on that what we have already calculated. The time taken for absorption is 10 to the power minus 15 seconds, very small time, right. So, that principle says the electronic transitions are so fast in comparison to the nuclear motion. Nuclear motions are slow relatively, right. It takes about a picosecond or more than that for nuclear motion, that immediately after electronic transition the nuclei have nearly the same relative position. So, nuclei does not move, right, during the electronic transitions. So, I have this particular diagram to explain you this Frank-Gordon principle, right. Here this axis is my nuclear axis, nuclear separation, and I have taken a very simple harmonic potential over here. So, this is my harmonic potential, just simple vibration of a diatomic molecule, that is it. So, now these are the different vibrational levels in this particular state and this state, right. These are 2 electronic levels of this molecule. So, obviously, as I said that in the ground state the molecule is most likely to stay in the V equal to 0 state, like V equal to 0 level over here. Now, when there is a transition from this state to the upper state, right, this state to the upper state, as you can see over here, right, the nuclear position, it is approximately 2 over here, that is remains same when you excite over here, that R value does not change. This R value does not change when you move from this level to the other level, R value does not change, right. This is the Frank-Gordon principle, right. So, I cannot draw this line like this way. It means the R value is changing during the transition, but Frank-Gordon principle says that the electronic transitions are ultra fast in nature. It is so fast that during transition the nuclei will remain as it is, nuclei will remain as it is. So, this is wrong. So, this transition is represented by a vertical arrow, right, vertical arrow, not a slanted one, right. So, this is not very difficult to understand. So, to make you understand, I have drawn these 2 harmonic potential again. This is in the ground state, denoted as ground state, this is in the excited state. So, these are this wave function, as you know, this harmonic potential wave function for V equal to 0 level looks like this, and as I have only the molecules or system present in the V equal to 0 level. So, I have just drawn only one wave function over here, but in the excited state the system can go anywhere, right, anywhere. So, it can go from V equal to V double prime equal to 0 to V prime equal to 0 or 1 or 2 and so on and so forth. So, once excitation, so this can go to here, here or here, right. So, this wave function I have just plotted over this 3 V value, V prime equal to 0, V prime equal to 1 and V prime equal to 2. Okay. So, now you look at over here, as the nuclei will not going to change its position during the transition, right, during the transition, that means its wave function will remain same, because these wave functions are nothing but the nuclear wave function, right. This is so the wave function will remain same, and the most likely transition will be the one that has most overlap with the excited state, because then they have to be same, they has to be same. So, from here to here, when the system will go from here to here, it looks that it reach that similar wave functions, right, whatever was present in the ground state. So, the intensity of this transition will be much more compared to this or this. So, obviously, in this case what we can see is that the 0,0 transition, which is denoted by here, right, 0,0 transition is strongly intense, but the 0,1 and 0,2 transitions are weak compared to the 0,0 transition. So, this is the typical measured absorption spectra of this molecule. Here you can see the clear observance of these vibrational features, and this 529 nanometer band is 0,0, and this is most intense band, right, and then the next band comes as 0,1 band, then 0,2 band, and so on. And we have another over here which corresponds to the S0 to S2, that means ground to the second electronic excited state, and so on. Okay. So, in this case the 0,0 transition was most allowed or transition, because the position of this this harmonic potential and the position of this harmonic potential, they are almost similar. However, if they are shifted, there is no guarantee that these two are exactly same, right. If they are shifted, like they are same here, but they could be shifted also at this position. Now, the minimum position here and this minimum position here, they are not same, right, they are not same, it is shifted. So, in this case, right, when I excite the system, this particular excitation will see a different overlap compared to the earlier, right, what I have shown. In this case, you see this overlap is most intense over here, because ultimately this is this wave function I have to make a square, right. So, this has a most overlap in this case. So, the 0,1 transition is most intense transition. Okay, so this is that relaxation which I will come later, right. Right now I am not talking about this relaxation part. So, this is the measured absorption spectra of another molecule, this is anthracene, and as you can see here, the 0,0 transition is less intense than 0,1 transition, which is a similar case like this, right, it is a similar case like this. Okay, so, now let me show you what is the instrumentation of this spectrophotometer. Well, the spectrophotometer is an instrument which is used to measure the absorption spectra, and I already explained you what is the absorption spectra. Absorption spectra is a plot of absorbance versus wavelength, right. So, I showed you that some typical absorption looks something like this way. That means I have to scan the wavelength and I have to measure the A. I have to measure the A. Measuring A means measuring I, right. So, basically what I have to do? I have to have this I0, I have my sample over here, this is my sample. After passing through become I, right. Do not forget that this is wavelength dependent, that means I have to somehow scan this wavelength. So, this is a function of wavelength, this is also a function of wavelength. So, I have to measure this I0 and I. How I am going to measure this I0 and I? So, first let me discuss the single beam spectrophotometer over here. So, this spectrophotometer again this term is the instrument used to measure absorption spectrum, right. So, there are two varieties of this instrument. The first one is being the single beam spectrophotometer. Okay, so in this instrument what we have obviously you have to generate the light of different wavelengths. So, I have a light source over here, so which could be a simple tungsten filament lamp, incandescent lamp which you see everyday life, depending on the choice of the wavelength, right. If I want the visible light from 450 nanometer to 800, 900, 1000 nanometer, then normal lamp is good enough, the tungsten lamp is good enough. If you want the UV, then you need a special type of lamp, because the tungsten lamp does not emit the UV light, right. Okay, forget about that. So, I need a lamp which can generate the choice of wavelength, So, light source able to generate choice of wavelength. Then I need something which is able to select your desired wavelength, right. Let us say this particular lamp can generate a wavelength of a wide region. So, for 450 nanometer to 1600 nanometer or something like that. So, so this is the lamp spectrum, let us say it is like this, wavelength versus intensity, simply, right, intensity, let us say it is like this. Here it is my 450 nanometer, here is my 600 nanometer, here is my 800 nanometer, here is my 1000 nanometer, and so on. So, but you need a particular lambda. So, you need some device which can used as a wavelength selector. So, I have a device, I just name it as wavelength selector. Actually, it is known as monochromator, that you have seen. If you used computer disk and you shine in white light like normal sunlight, then you see Vibgeo, right. So, that means the white light is converted into different color, that probably also you have seen in your high school, right. So, that prism, right, prism can convert the white light into its corresponding colors. So, this is the similar type of device, and there is a way that at your desire you can choose your color of light. You said that in this device that I want 500 nanometer, this device will only give you this 500 nanometer light, right. So, at per your choice this device will select your wavelength, right. Okay, so time is up. So, we will continue our discussion in the next class. Thank you.